Okay, so my name is Omar Fridleifsson, and my co-authors are Wilfred Elders and Robert A. Schierenberg. And we are all geologists and therefore our focus within the ITDP has been on geology, plus a lot of other things. We have been serving as PIs mostly for coding from PIs for the ICTP fund or grant, and also for National Science Foundation grant. And we have been at this project from the beginning, really for 20 years. Now, the idea with this paper is just to talk about the success story and the lesson learned, a quick overview, and what next steps are needed to take for commercialization. Now, the 3 drill sites that we have been focusing, or the program has been focusing on, is Krafla in Northeast Iceland, where ITDP-1 was drilled, and then Reykjavis down here at the tip of the Reykjavis Peninsula, and the third one, the ITDP-2 is located, and the third one at the Hengill system, which will be described in next talk. Now, the basic idea with the ITDP drilling project, as you probably all know, is to drill deep enough into the roots of the high temperature hydrothermal system to produce water at supercritical condition and bring it to the surface as 400 to 600 degree superheated steam, and to study the feasibility and economics of extracting energy and possibly chemical from the hydrothermal system at these supercritical conditions. And this hasn't changed, still is the basic idea. Now, we have published a lot. We drilled into Magma in 2009, and we created the world's first Magma ETS system. And we had described all this in a special issue of Geothermal in 2014, and also in the sessions and many papers at the World Geothermal Congress in Australia. So you can read all about it, it's all published. This is a view to the drill site in Krafla. But the fact sheet, the original plan was to drill it down to 4.5 kilometers. The drilling took place in 2008 and 2009, and after several difficulties, and after having got stuck twice and sidetracked in both cases, we had to terminate the drilling as we had 3 times drilled into Magma, but we didn't know for the first 2 times because of total circulation loss, so we didn't see what we were drilling into, but we got a kick on the drill string, and after some 2 hours we finally got some return to the surface and got some rhyolitic glass coming up, and then we realized that we were in Magma. Now, instead of just put a cement plug in the well, the ITDP consortium decided to float test the well and inserted a sacrificial casing, cemented it down towards the bottom, but had a 100 meter roughly open perforated liner closest to the Magma. Then a successful float test was conducted for 2 years, and the hostile fluid chemistry was analyzed and successfully dealt with. And at that time, the ITDP became the world's hottest production well, 452 degrees. A superheated steam at a wellhead pressure of 14 megapascals. Now, the sequence of event was roughly this. During drilling and water stimulation, a metamorphic aureole above the Magma pocket was thermally cracked. And then after heat up and float test, for the float test, and by opening the well, a reservoir fluid from above, because we are just in the reservoir, conventional reservoir, which roughly is about this temperature 340, just about where we were. It was attracted downwards towards the Magma interface, something like this, and heated up by 100 degrees to 450 degrees. Now, and then we float this 450 degree hot superheated steam to the surface, and interestingly, it left the casing intact. Once it was super dry, it was wet before because of the drilling fluid, and then finally we got a dry steam up to the surface, and this superheated steam was then cleaned after some experimenting and all sorts of analysis, cleaned by wet scrubbing, driving elements like chlorine, sulfur, and silica into the fluid phase and leaving pure steam for power production. So that was quite a successful thing. We actually managed to drill into magma. Now, our pilot test was experienced for 2 years, and you can see the layout here, the wellhead, the 2 master valves, and then several valves, top of flow line, and then in the containers, there were some wet scrubbing experiment and other experiments. Some of this has already been mentioned, like before here, but the main thing is that we got rid of all the corroding elements like chlorine and sulfur and silica particles with pressure dependent on deposits, but that dust could also be removed into the water phase. And it was so efficient that the full-size equipment was being designed for power production by the power company to scale it up to take it into line to the Krafla power plant. But before that happened, after 2 years experiment, one of the valves here on the top of the Christmas tree needed a replacement, and then we needed to close the 2 masters valve, which both of them failed. The stem broke, and the only way to control the valve was really to use water, cold water, and with that effect, even though they did it carefully, the casing was severely damaged, and it was impossible to recondition the well after this, and it was finally filled by cement. So that was the fate of the well, but for sure we can repeat this and do it with a better equipped, shall we say. Now, turning now to the ITDP2 at Reykjavis in 2016, we started drilling the well. It took only about 5 months, but Reykjavis is here at the tip of the peninsula where the Reykjavis ridge comes to shore. And you can see here the ocean floor and the mid-Atlantic ridge here. And we are really drilling into geological setting, which are analog to the root zones of the black smoker systems. Into extreme temperatures, and which was surely unprecedented and now for sure rewarded this drilling effort. Now the well was drilled to 4,650 meter depth, and as it was inclined, it's 4.5 kilometers through from vertical, and you can see the rigs on site, and we inclined the well towards the south into the center of the field. The drilling itself took only about five months. Then we did some deep injection for the supercritical part of the system for 5 months, and then continued with cold injection for over a year, and then finally hot injection for heating up before a flow test, which was planned. But all this has been described in the literature, so we don't have time to go into detail, but I particularly want to point out the most recent one, Berg et al. In 3G, and you have an access sheet to the open access paper, and the second paper also of key importance here is Bali et al. In geology, also an open access, and at the World Geothermal Congress in October last, we had 27 papers there, and several other papers open access. You can all look into this, and this will be left in with the presentation here. But looking at the well track, it was from surface here down towards the bottom. You can see some dots here with all our circulation feet points, various size. But the drilling itself to this depth was quite a successful operation with mud motor, and amazingly successful, and the cementing as well of the casing down to roughly almost 3 kilometers looked very successful as well, but proved not to be, as we had observed the casing failure against the former feed shown in the original production well that we were deepening. Now, other things were successful, like looking well tripping, and the coring was quite successful as well. But what's the surprising thing was really the total loss of circulation for almost all the time during drilling, so it didn't hardly get any drill cuttings at all. We tried to heal the loss zones, but that was not curable, even with 12 plug cementing jobs. So we decided to do blind drilling for the rest of the hole. Here is a diagram just showing the plan and the following and the reality. We almost followed the plan. This was delayed due to the cementing of the lost circulation zone, but these are the overview of the cores, and the best cores we got from the very bottom of the well. But during drilling and after finishing the 12.25 well down here, we did some logging trip and also saw some unmeasured or logged supercritical conditions at the very bottom of the well. You can see the temperature log down here and the pressure log, the blue one, and feed points here, quite clear. Now we continued after putting a liner into the well, and then we had a deep injection for a while and deepened the well first down for a couple of 100 meter more, and got 3 successive drill cores from the very bottom with very good core recovery, which is a key issue. But when we were logging the well after the deep injection, we discovered that the casing damage, roughly this is a diagram here from 2.2 to 2.4 kilometers, and a CCL log, casing color log, we show that the casing was damaged and the inflow of water from the conventional reservoir at say 2 to 2.3 kilometers to 2.4 represented here. Simplicity, but the main feed zone was down at 3.4. You saw this on the first day at the symposium, that this was discussed, these 3 zones. This was not intended. This one was actually subcritical, and then feed points at the very bottom, and several of them down towards the very bottom. And it was quite clear for us that this one would be the dominating feed as we started to produce, as it was much bigger than the deeper one. So ideally we should have cased this down to 3.5 kilometers or below this feed point. Okay, but the main surprise is this high permeability during all the time and this total loss of circulation. We didn't get any drill cuttings, but so without the drill cores we would have known nothing about the rock types and their hydrothermal alteration and metamorphism. So this was a key element for us to get the cores. Now we could do some geophysical logging with the LVT tool and from Weatherford, which was successful, and about this great permeability to great depths. It really opens new dimensions for re-injection into the super hot rocks or ultra hot rocks. It would give pressure support for the overlying reservoir, the conventional one, and also temperature support. So it could lengthen the lifetime of the Reykjavis system if we manipulate a little bit with injection, but we also may possibly be able to produce from this, and this is a key question which remain to be answered. Now the petrology of the drill cores from the very bottom here, this was the drill bit that we used last time. You see some fracked drill cores of igneous rocks, diabase. Here is an open mineral vein coated with quartz and biotite. And interestingly, when we drilled into this with this bit, and the drilling fluid mixed with the supercritical fluid inside the open fracture and oxidized it almost instantly and coated it with hematite or iron oxide. And it's in these quartz that the fluid inclusion studies were mostly done that tell us a lot in one of these about the temperature condition of the present day. Now, the key information from the petrological and fluid inclusion data show that the rock is pervasively altered at 800 degrees in the presence of supercritical altered seawater. The present day temperature at 4.5 kilometers is roughly 600 degrees. And the fluid inclusions and mineral composition record the presence of vapor and the high salinity supercritical brine during rock alteration. And this lower salinity, low viscosity vapor-like fluid completely permeated the apparently impermeable rock. So it is just like the water was permeating the rock like an ink into a blotting paper. So this was really a surprise. It was completely altered. And this is all described in, say, Robert Schellenberg's 3G papers, which I recommend strongly, as well as the Bali paper. But the key question for the ITTP program in general concerns this separated vapor-like phase. Can such a clean fluid, shall we say, at supercritical condition be tapped through drill holes for electric power generation? And this is a key question and remains until we have done this again. But we do know that both from the ITTP2 well that it is both a natural and induced fracture permeability of significance and clear evidence for massive pervasion of superhot aqueous fluid through the hot rocks. Now, next steps. What's needed? Now, this is a picture of the flow line and the wellhead at Reykjavis at ITTP2. And we believe this wellhead and flow line design and construction is of sufficient quality to enable continuation of the ITTP program without much modification. The wet scrubbing pilot plant in Krafla was tested in 2012 on the full-scale plant design, so that can be repeated in Krafla for sure. We are sure. But the weak points on both sides for continuation of the ITTP project mostly concern the casing quality and the proper cementing procedures. Drilling, say, deep wells into supercritical regime, or magma for that matter, does not appear to be a major problem, nor a showstopper. So we can continue with some improvement. And I'm not a salesman, but a casing material for ultra-hot wells is now available on the market. It's Timetal 475, a new titanium alloy for high-power deep geothermal wells, so very highly corrosion resistant and immune to H2S or elemental sulfur embrittlement, etc., etc. Seem to be the proper material for the production casing at least. And also developed in the DPDS project or program, projects, so to say, prototype flexible couplings have already been designed, tested, and manufactured, and they can be produced whatever material you choose, be it Timetal 475 or something else. So we have some solutions that to be tested for the weak points. We still need to think about the semantic protocol and process. But the ITTP and ITTP2 have surely paid off by increased and valuable knowledge and understanding. EGS systems can be created in superhot rocks at Reykjavis and without doubts in many other systems. And Magma EGS can be created at shallow depth in Krafla and probably in many other places. Permeable rocks are found down to great depths, and permeability is enhanced by thermal cracking or hydraulic cracking. A combination of both and supercritical saline systems are drillable and usable, we believe, for power production. The next steps for commercialization, recent technical advances in casing material and coupling should enable continuation of the ITTP. Cementing procedures need be scrutinized for satisfactory results, be it through state cementing, reverse cementing, material selection, or combination of all. This, of course, is for the drilling engineer or drilling engineers. So you have to leave it for them to consider very, very, very seriously, which I know they have done already. Most of the drilling engineers in this super hot business. And material selection for surface installation for power production should not be a problem, apparently. So our message to the geothermal industry, just continue the ITTP research and development project to conclusion and claim your reward. So ITTP3 will be discussed in next talk, but we are hoping that it will be realized within 5 years. And with this picture from Reykjavis, I just say thank you for your attention.